On a clear October night in 1923, a man stood at the eyepiece of the world's most powerful telescope and stared into something the size of a thumbnail held at arm's length, a faint smear of light in the constellation of Andromeda. He had been staring at it for months. He thought he understood it. Then he noticed a single star winking at him, and everything changed, not just for him, for everyone, for the entire human conception of the universe. 100 years later, a telescope named for that same man has spent more than a decade doing something that no instrument in history has ever done. It has stared directly into the face of the Andromeda galaxy, our nearest large galactic neighbour, 2.5 million light-years away, and resolved it, star by star, into a mosaic containing 2.5 billion pixels of data, 200 million individual suns, catalogued, measured, aged. And what Hubble found was not what anyone expected. Andromeda was supposed to be a twin of our own Milky Way, born at the same time, in the same cosmic neighbourhood, from the same primordial material. It was supposed to be a stable, orderly spiral galaxy, serene, predictable, rotating on its axis with quiet gravitational dignity for the next several billion years before gently bumping into us. Instead, what Hubble found was a galaxy that looks like it has been through a war. A galaxy that formed stars in a violent, frantic burst and then suddenly stopped. A galaxy haunted by the scars of a collision so catastrophic that it stripped away a companion galaxy almost entirely, leaving only its naked core orbiting Andromeda like a trophy. A galaxy whose centre hides a black hole, surrounded by a disk of stars that should not exist, formed in conditions so hostile that star formation was supposed to be physically impossible. And, perhaps most unsettling of all, a galaxy that is already touching us, right now, tonight. Its halo of diffuse, invisible gas extends so far across space that it has already crossed the halfway point to the Milky Way, and in some directions it reaches all the way to our own front door. Andromeda is not waiting for us, it is already here. To understand why Hubble's findings carry such weight, you first need to understand the relationship between our galaxy and Andromeda, and why astronomers have spent the better part of a century treating it as the most scientifically precious object in the sky. Andromeda sits at a distance of approximately 2.537 million light-years from Earth. That number, rendered in kilometres, is 24 quintillion, a quantity so large that it becomes meaningless without a frame of reference. A more useful way to hold it is this. If the Milky Way were the width of a dinner plate, Andromeda would be sitting on the table beside it, roughly 25 plate widths away, close enough to see clearly, far enough to qualify as a genuinely separate empire of stars. The galaxy is formally designated Messier 31, Messier being the French astronomer Charles Messier, who catalogued it as a fuzzy object in 1764 that definitely was not a comet. The designation M31 appears throughout the scientific literature with the casual frequency of a postal code, but the name tells you almost nothing about the actual scale of the thing. Andromeda contains an estimated 1 trillion stars. That is roughly twice the stellar population of the Milky Way. It stretches approximately 152,000 light-years from edge to edge. On the night sky, even from 5 million light-years away, it spans an angular diameter roughly 6 times that of the full moon. The reason most people have never seen it with the naked eye is not because it is small, it is because it is genuinely faint, spread thin across a wide arc of sky, and our eyes are not tuned for its particular dimness. But it is there, every clear autumn night, a faint oval smudge near the top of the constellation Perseus, the largest single object visible to the human eye, and almost no one knows it exists. For most of the 20th century, the relationship between our galaxy and Andromeda was understood in comfortingly simple terms. They were siblings, both spiral galaxies, both containing roughly 1 trillion stars, both embedded in the same gravitational structure called the local group, a loose cluster of around 54 galaxies, of which the Milky Way and Andromeda are by far the dominant members. They had formed at approximately the same epoch, roughly 10 to 13 billion years ago, from the same vast filaments of primordial hydrogen and helium that collapsed under their own gravity in the aftermath of the Big Bang. They had evolved in parallel, side by side, through the same 13.8 billion year history of cosmic time. The scientific consensus, maintained through most of the 20th century and into the early 21st, was that whatever you learned about Andromeda, you were essentially learning about our own galaxy by proxy, because we are embedded inside the Milky Way. Like trying to understand the layout of New York City while standing in the middle of Central Park. As one astronomer memorably put it, we can never step outside and photograph our own galaxy whole. Andromeda offered the next best thing, a full disk view of a spiral galaxy similar to ours, close enough to study in unprecedented detail. Its stellar populations, its structure, its star formation history, its merger events, all of this was assumed to approximate our own. Study Andromeda and you study us. That assumption is now in serious trouble, because when Hubble finally assembled the most comprehensive photographic portrait ever made of another galaxy, a decade in the making, over 1,000 orbits around the Earth, 600 separate fields of view stitched into a single 2.5 billion pixel tapestry, it did not show a galaxy at peace. It showed a galaxy that had been through something violent, something transformative, something that left marks so deep they are still visible today in the ages and distributions of individual stars spread across a disk 152,000 light-years wide. But before we can understand what Hubble found, we need to understand how remarkable it is that Hubble, or any telescope, could see it at all. That story begins with a single annotated glass plate, a man who changed our understanding of the universe in a single night, and the curious historical echo that connects his discovery directly to ours. On the night of October 5th to 6th, 1923, Edwin Powell Hubble was working at the Mount Wilson Observatory in the San Gabriel Mountains, above Pasadena, California. He was using the Hooker telescope, at that moment the largest working telescope in the world, with a primary mirror 100 inches in diameter, built from a single piece of glass cast in Saint-Gobain, France, and floated across the Atlantic on a ship that had to be specially insured against the catastrophic consequences of losing it. Hubble had positioned this instrument towards the Andromeda Nebula, as it was then called, because the prevailing scientific consensus of the time held that it was a gas cloud somewhere inside or near the edge of the Milky Way, a smear of unresolved light. Pretty, but local, Hubble had been examining Andromeda for weeks, comparing photographic glass plates taken on different nights, looking for novae, stars that flare suddenly in brightness and then fade. He found what he thought were three. He scrawled a large letter N on each of the three suspect stars on his plate, designated H335H, Hooker Plate 335 by Hubble. Then he went back to compare earlier plates to make sure, and that was when he noticed something that stopped him mid-annotation. One of the three N marks was wrong. The star he had labelled a nova was not brightening explosively and staying bright. It was pulsing, rising and falling in a slow rhythmic cycle, brightening and dimming with clockwork regularity. It was not a nova at all, it was something far more significant. He crossed out the N with a thick dark line and wrote, in capital letters, just two words, VAR, short for variable. What Hubble had found was a Cepheid variable star. Cepheid variables are an extraordinary class of pulsating supergiant stars whose period of pulsation, the time it takes to complete one full cycle of brightening and dimming, is directly related to their intrinsic luminosity. This relationship had been discovered by astronomer Henrietta Swan Leavitt in 1908, working at the Harvard College Observatory, where she had catalogued hundreds of Cepheids in the Magellanic Clouds and noticed the critical pattern: brighter Cepheids pulse more slowly. If you know a star's period, you can calculate how bright it truly is. And if you know how bright it truly is and compare it to how bright it appears from Earth, you can calculate exactly how far away it is. Cepheids are, as astronomers call them, standard candles, lighthouses of known wattage, allowing you to triangulate cosmic distances with precision. Hubble knew immediately what he had. He spent the following weeks calculating the Cepheids' period by examining every available earlier plate of Andromeda he could find, building up a light curve that showed the star cycling through its pulsations with a period of 31,415 days. From that period, he derived its intrinsic luminosity. From that luminosity, compared to its apparent brightness in the photographic plates, he calculated a distance. The number he arrived at was approximately 930 light years, a figure that would be revised upward over subsequent decades to the current accepted value of 2.537 million light years. But even at his original calculation, enormous enough to place Andromeda unambiguously beyond any possible boundary of the Milky Way. On the same plate where he had crossed out the N and written VR, Hubble wrote a note in the margin. It read simply, "This is a Cepheid!" 2 exclamation marks. And then below the number he had calculated, the distance, written out by hand in pencil with the calm understatement of a man who has just proven that everything his colleagues believed about the boundaries of the universe was wrong. He sent a letter to Harvard astronomer Harlow Shapley, who had argued passionately for years that the Milky Way encompassed the whole of the observable universe, that Andromeda was merely a local curiosity. Shapley reportedly read the letter and said quietly, "Here is the letter that has destroyed my universe." He was not wrong. He was also not wrong in the most magnificent way possible. Overnight, literally overnight, in the period between the photographic plates of October the 5th and the calculations of the days that followed, the universe expanded from a single island of stars to an infinite ocean of island universes, each one an unimaginable empire of suns. This is, to my mind, one of the single most consequential moments in the history of human thought. Not just in astronomy, in all of human intellectual history. The universe did not just get larger the night Edwin Hubble crossed out that N, it got incomprehensible. And our place in it, the Earth, the solar system, the Milky Way, was reclassified in a single pencil stroke from the entirety of creation to a single grain of sand on an infinite beach. Now here is the paradox that drives everything that follows. That single discovery should have made Andromeda the most intensively studied object in astronomical history. And in some sense it did, but for decades we could only study it in fragments. Ground-based telescopes could show us the galaxy's broad shape, its rotation, its overall brightness profile. But the individual stars, the actual grains of sand, blurred together into an unresolvable smear. To study Andromeda's history at the level of individual stellar populations, to read the actual biography of the galaxy, written in the ages and compositions of its suns, required something that did not yet exist. It required a telescope in space. One with a mirror precise enough to correct for the shimmering blur of Earth's atmosphere. One with a sensitivity broad enough to capture light from near ultraviolet to near infrared, reading stellar temperatures and compositions with spectroscopic precision. One with enough orbital time to stare at 600 separate overlapping fields of view over more than a decade and stitch them into a portrait complete enough to tell a story. It required, in other words, Hubble, the telescope named for the man who discovered the universe's true size by staring at the very same galaxy. The historical echo of that is not something I can let pass without noting it. The Space Telescope named for Edwin Hubble, launched in April 1990, has now completed a decade-long survey of the galaxy that Edwin Hubble made famous, and found inside it evidence that the universe is even more violent, more complex, and more turbulent than Edwin Hubble himself could have imagined. But even as that survey was beginning to yield its results, a separate team of astronomers had already found something deep in Andromeda's core that nobody could explain. Something that should not have been there, something that the most basic laws of astrophysics suggested was physically impossible. And that problem, the paradox at the heart of Andromeda, was about to become considerably more complicated. There is a zone around every supermassive black hole where the physics of star formation breaks down completely. This is not a suggestion, or a model-dependent approximation, or a theoretical grey area subject to revision. It is a hard consequence of gravity. As you approach a black hole, the difference in gravitational pull between the near side and the far side of any given object. What physicists call the tidal force increases with terrible rapidity. At small enough distances, these tidal forces exceed the self-gravity of any cloud of gas or dust, attempting to collapse and form a star. The cloud gets stretched apart before it can hold itself together. The threshold at which this happens has a name: the tidal disruption radius. Inside it, star formation is impossible. The black hole shreds the raw material before it can do anything useful. The supermassive black hole at the centre of Andromeda was first proposed in 1988, independently, by John Cormendy of the University of Texas, and by the team of Alan Dressler and Douglas Richstone, all working from ground-based observations of the velocities of stars near M31's core. Stars near the centre of Andromeda were moving far too fast to be accounted for by the combined gravity of everything visible. Something invisible and enormously massive was hiding at the centre, whipping those stars around at velocities that could only be explained by a dark, compact object. The team estimated its mass at tens of millions of solar masses. The simplest explanation was a black hole, proving it unambiguously, ruling out every alternative hypothesis. Every exotic theoretical substitute was another matter entirely. Then, in 1993, Hubble turned its eye towards Andromeda's core and found something that made the black hole question seem almost secondary by comparison. A team led by Todd Lauer of the National Optical Astronomy Observatory, working with Sandra Faber of the University of California at Santa Cruz, aimed Hubble at the centre of M31 and found two distinct peaks of stellar density where there should have been one. Andromeda's core appeared to have a double nucleus, two separate clusters of stars, approximately 5 light-years apart, both sitting within the galaxy's central bulge. This was deeply confusing. Two stellar clusters that close together should merge into one within a few 100,000 years. Gravity would have pulled them together long ago. Yet there they were, two distinct peaks, P1 and P2, staring back at the telescope with unambiguous clarity. The explanation for the double nucleus took nearly a decade to arrive. Scott Tremaine of Princeton University proposed that the two apparent peaks were not actually two separate clusters at all. What Hubble was seeing was a single, highly eccentric ring of old, red stars orbiting the black hole on an elongated elliptical path, like a very stretched halo or an off-center garland, because the stars on the ring spend more time near the outer edges of their orbits, just as planets slow down when they are farthest from the Sun. The stellar density appeared highest at the two ends of the ring's major axis. When viewed from our particular angle, with Andromeda tilted 77 degrees relative to our line of sight, those two bright ends appeared as two separate blobs. The double nucleus was an optical illusion, an artifact of orbital mechanics seen from a particular vantage point. P1 was the brighter, more distant apparent peak, containing the majority of the ring's visible stars. P2, the dimmer, closer peak, was where the black hole actually sat. This explanation was elegant, and it satisfied the double nucleus problem. But in 1995, astronomer Ivan King of the University of Washington was studying the same region with Hubble when he noticed something new: an unusual blue glow at the very centre of P2, right at the position of the black hole itself. Blue light from a stellar population means one thing: hot, young, massive stars. But these stars were sitting essentially on top of a supermassive black hole inside the tidal disruption radius. They had no business being there. By 1998, Lauer and Faber had confirmed that the blue glow was not a single star or an artifact of the data. It was a compact cluster of genuinely young stars. The cluster was tiny, occupying a region less than a light-year across, and it sat so close to the black hole that the tidal forces from that object should have made it completely impossible for any of its constituent stars to have formed in place. Yet they had formed roughly 200 million years ago. Hubble's Space Telescope imaging spectrograph confirmed it unambiguously in 2005. The cluster contained at least 400 individual blue stars, all formed in a single burst of activity approximately 200 million years ago. all whipping around the black hole at a measured velocity of 3.6 million kilometers per hour, fast enough to circle the entire Earth in 40 seconds. And that black hole, its mass now nailed down by the velocities of those stars, weighed in at 140 million times the mass of our Sun. This is the number that matters, 140 million solar masses. That is the confirmed, observationally constrained mass of Andromeda's central black hole. For comparison, the Milky Way's central black hole, Sagittarius A, weighs approximately 4.1 million solar masses. Andromeda's central engine is more than 30 times more massive. Andromeda is, in this sense, a more extreme galaxy than our own, and it has been at some point in its past far more active, but the blue disk of stars remained an enigma. How do you form stars in a place where star formation is physically impossible? The answer that astronomers have converged on, and it is still an answer that carries a significant asterisk, is that the stars did not form where they now orbit. They may have formed further out, in a gas disk large enough and dense enough to shield its inner regions from tidal disruption, and then migrated inward through gravitational processes that are still not fully understood. Or the gas from which they formed may have arrived in a single large, coherent clump rather than a diffuse cloud. A bolus dense enough to resist tidal disruption during its infall, compressing rapidly and triggering star formation before the black hole could tear it apart. Neither explanation is fully satisfying. Todd Lauer captured the scientific community's collective puzzlement with memorable honesty when he told reporters, "Seeing these stars is like watching a magician pull a rabbit out of a hat. You know it happened, but you have no idea how." What this puzzle revealed was something deeply important about Andromeda's character. Its centre was not quiet, its centre was not stable. Something had driven a burst of star formation there in an environment of almost unimaginable violence, approximately 200 million years ago. And that timing, 200 million years, is a number that kept appearing in other contexts as well, a figure that, in the light of the survey data that would eventually arrive from the PH-TAN and PEST programs, would begin to look less like a coincidence and more like a clue, because the blue disk at Andromeda's core was not the only evidence of a catastrophic event in M31's recent past. The surface of this galaxy, when examined with the sensitivity Hubble's mosaic now provided, was covered in scars, vast streams of stars, arcing across the halo in geometrically improbable trajectories, carrying the gravitational fingerprints of disrupted companion galaxies. A star formation history utterly unlike our own, frantic, then abruptly silenced, like a sentence that ends in mid-word. And at the centre of all of it, a small, compact, peculiarly dense galaxy currently orbiting Andromeda, a galaxy so stripped and reduced that only its naked core survived the encounter that destroyed it. A galaxy whose name is Messier 32, and whose role in Andromeda's story astronomers now believe may be the most consequential single event in our galactic neighbourhood in the past 5 billion years. The stakes here were about to climb significantly higher, because the same collision that traumatized Andromeda also left behind a forensic record written in the ages of stars. And reading that record required a man named Daniel Weiss, a decade of Hubble time, and a willingness to follow the data wherever it led, even when it led somewhere genuinely alarming. When Daniel Weiss at the University of California, Berkeley, described the Andromeda galaxy to reporters in January 2025, he did not reach for the careful, hedged language of a cautious scientist. He said, "Andromeda's a train wreck. It looks like it has been through some kind of event that caused it to form a lot of stars and then just shut down. This is not the description you expect from an astronomer discussing the galaxy that serves as the benchmark for all spiral galaxy research." But Weiss was not being hyperbolic. He was being precise, because that is exactly what the data shows. To understand the finding, you need to understand what the PH-PAT and PEST surveys actually accomplished. Astronomers have long been able to study distant galaxies as blurred, unresolved smears of light, measuring their total luminosity, their overall colour, their rotational velocity. These bulk measurements tell you something about a galaxy's properties, but they cannot tell you the story of individual stellar populations. They cannot tell you how old the stars are, or what they are made of, or whether they formed in a single burst or in a steady trickle over billions of years. Andromeda, because of its extraordinary proximity, offered something no other large galaxy in the universe can offer: the ability to resolve individual stars within its disk. Not all of them. Andromeda's trillion-star population far exceeds Hubble's sensitivity limit, but the brighter ones, stars hotter and more luminous than our own Sun, catalogued one at a time, their colours and brightnesses measured with enough precision to place each one on a diagram called the Hertzsprung-Russell diagram, which functions as a stellar age chart. The position of a star on that diagram, its colour relative to its brightness, tells you approximately how old it is, how massive it is, and how far it has progressed through its nuclear-burning life cycle. Do this for 200 million stars, distributed across the entire disk of a galaxy, and you have something extraordinary: a population map. A colour-coded archaeological survey of the galaxy's entire star formation history, written in the actual ages of individual stars, still burning in the disk today. The panchromatic Hubble Andromeda Treasury, PAT, began accumulating this data around 2012, mapping the northern half of Andromeda's disk across 6 wavelength bands simultaneously: near ultraviolet, 2 visible bands, and 3 near-infrared bands. The multi-wavelength approach was critical because different wavelengths are sensitive to different stellar temperatures and compositions, allowing each star to be characterized with far greater confidence than any single band measurement could provide. The survey required 828 Hubble orbits. Each orbit lasted approximately 97 minutes, during which Hubble took exposures of a specific pointing, then moved on to the next overlapping field. The resulting dataset covered roughly 1/3 of Andromeda's star-forming disk. Then came PAST, the panchromatic Hubble Andromeda Southern Treasury, led by Zhuo Chen at the University of Washington, adding the southern half of the disk in 195 additional orbits, imaging approximately 100 million stars. The southern half is particularly scientifically valuable because of its structural properties. It is more sensitive to the signatures of merger events, to the asymmetries and distortions that a major collision would have left behind, to the patterns of star formation that a galactic encounter would have triggered or suppressed. The combined dataset, released in January 2025 as a single photomosaic of 2.5 billion pixels, represented the culmination of over a decade of work and more than 1,000 total Hubble orbits. What the combined data revealed, when astronomers began reading the star formation history encoded in those 200 million catalogued stars, was a pattern unlike anything observed in the Milky Way. In our own galaxy, star formation has proceeded in a relatively steady, continuous way over billions of years. There are variations, local bursts, regions of more or less activity, but the overall trend is a relatively smooth, declining rate of star birth spread across the entire disk, without any dramatic interruptions. The Milky Way is a fairly well-behaved spiral galaxy. Its evolutionary history, inferred from stellar population studies and models, looks like a long, gradual story of slow galactic maturation. Andromeda's history looks nothing like this. What the PA's past data reveal is a galaxy that formed stars at a high rate through much of its early history, then continued at a lower level, and then, at some point within the last few billion years, experienced a significant event that left behind an anomalous stellar population. The disk of Andromeda is more populated with younger stars than the Milky Way's disk would be at comparable ages. There are coherent streams and filaments of stars distributed through the halo and disk in patterns that betray tidal disruption, the gravitational shredding of a satellite galaxy. The star formation rate is lower today than you would predict for a galaxy of Andromeda's mass. It is, in the memorable phrase of Ben Williams of the University of Washington, a galaxy that looks like a transitional type between a star-forming spiral and a sort of elliptical galaxy dominated by aging red stars. This is startling, Elliptical galaxies, the large, featureless, football-shaped galaxies that tend to dominate the centres of galaxy clusters, are dead in the sense that they no longer form significant numbers of new stars. They used up or expelled their gas reservoir, and without gas there can be no star formation. The conventional pathway to becoming an elliptical galaxy runs through a major merger event, a galaxy collision so violent that it drives a burst of extreme star formation, burns through the available gas reservoir in a short, furious period, and leaves behind a system too depleted of fuel to make new stars at anything but a trivial rate. Andromeda appears to be partway through that process. It is not yet an elliptical. It still has a disk, still has residual star-forming activity, still makes a modest number of new stars each year. But the evidence in its stellar populations suggests it has undergone at least one major interaction within the past few billion years. An interaction that triggered an elevated period of star formation and then began the process of depleting the galaxy's gas reservoir. This was probably due to a collision with another galaxy in the neighbourhood, Wires said. The suspect in that collision is a small, dense, almost pathetically diminished galaxy currently orbiting just 24 light years from Andromeda's centre, Messier 32, and the story of what Messier 32 actually is, and what it once was, represents one of the most extraordinary forensic reconstructions in modern astrophysics. Messier 32 is visibly peculiar. It is an elliptical galaxy, classified as a compact elliptical, meaning it is extremely small and extremely dense for its stellar mass. Its central stellar density is among the highest measured for any galaxy in the known universe. Stars inside M32's core are packed so tightly that if our solar system were transplanted there, the nearest star to our Sun would be less than 1 light-year away. In our current galactic neighbourhood, the nearest star to our Sun is approximately 2 light-years distant, a gulf that Andromeda's core renders almost quaint by comparison. The compactness of Messier 32 is a clue. Compact ellipticals of M32's type are theoretically understood as the stripped-down cores of once larger spiral or lenticular galaxies. Galaxies that have been run through the gravitational gauntlet of a close encounter with a much more massive companion which strips away the outer stellar halo and disk, leaving behind only the dense central nugget. The tidal forces of the larger galaxy act like a cosmic lathe, peeling away layer after layer of the smaller galaxy's outer structure until only the fortified core survives. A 2018 study led by Richard de Souza of the Vatican Observatory, published in Nature Astronomy, used N-body simulations to reconstruct Andromeda's collision history, running the numbers on what kind of event could have produced the giant southern stellar stream. A coherent river of stars flowing through Andromeda's halo at tremendous distance, while simultaneously accounting for the elevated star formation rate in Andromeda's disk, the asymmetric distribution of stellar populations between the northern and southern halves, and the peculiar structural properties of M32. The simulation pointed to a large satellite galaxy, christened M32P by the team, that would have been the third largest galaxy in the local group at the time of its encounter with Andromeda. M32P would have had a stellar mass approximately 20 times the current mass of M32, making it a major galaxy in its own right. A galaxy that may have harboured its own satellite galaxies, its own complex structure, its own billions of years of stellar evolution. The collision that shredded it to the stripped core we now call M32 occurred, the simulations suggest, roughly 2 billion years ago. I will admit that when I first absorbed the implications of this reconstruction, I had to step back from the data and simply sit with what it meant. Messier 32, that faint, unremarkable smudge, visible in any modest amateur telescope as a companion spot to Andromeda's core, is the surviving remnant of what was once a galaxy 20 times more massive. A galaxy with its own history, its own stars, its own story, stripped to its bones by Andromeda's gravity, reduced to a dense compact ghost orbiting the scene of the collision that destroyed it. Every time you look at M32, you are looking at the fossil remains of a galactic catastrophe. The galactic graveyard is hiding in plain sight, the stars that M32's progenitor brought with it, the hundreds of billions of stars stripped from that spiral galaxy's disk and halo, are still out there, scattered through Andromeda's own disk and halo in coherent streams and asymmetric structures that the PAT and PAYAST surveys have now catalogued in extraordinary detail. Those are the younger stars that fill Andromeda's disk beyond what its own unperturbed star formation history would have generated. Those are the stars that make Andromeda look like a train wreck. Those are the stars that make it look transitional, heading, on geological timescales, from spiral to elliptical. But while the collision history of Andromeda's disk was being assembled from the P8HAT and PAST stellar population data, a completely different team of astronomers was discovering something equally remarkable about Andromeda's outer regions. A discovery so large, literally so physically enormous, that it changed how astronomers think about the true size of galaxies, and what they found was invisible, which is precisely why no one had found it before. Every large scientific discovery rests on a foundation built by people who never lived to see what their work would eventually reveal. This is the economy of science. The tools that enable one generation's breakthrough are almost always the creations of another generation's patience. The story of Andromeda is no exception to this rule, and the human story buried deepest in its science belongs to someone who spent her career cataloguing stars on photographic glass plates in a room at the Harvard College Observatory, working for a daily wage lower than the office cleaners, never given a faculty position, never promoted to a professional rank commensurate with the magnitude of what she found, and whose discovery made every subsequent measurement of cosmic distance possible. Her name was Henrietta Swan Leavitt. Leavitt was born in Lancaster, Massachusetts in 1868. She studied at the Society for the Collegiate Instruction of Women, what would later become Radcliffe College, the female counterpart to Harvard, and graduated in 1892. She had developed a passionate interest in astronomy, and after a period of illness that left her significantly hard of hearing, she volunteered at the Harvard College Observatory in 1895, then was hired at the rate of 30 cents per hour. Her job title was computer, not in the sense we use that word today. In the late 19th century, a human computer was a person, usually a woman, because women could be paid less than men for the same painstaking analytical work, who performed the laborious numerical calculations required to analyse photographic plates. Harvard's observatory director, Edward Charles Pickering, had assembled a group of women computers who became known, often condescendingly, as Pickering's harem. Leavitt was among the most talented of them. Her assignment was the small and large Magellanic Clouds, dwarf satellite galaxies of the Milky Way visible in the southern sky, where she was tasked with cataloguing variable stars. She worked from photographic glass plates, examining each one under a magnifying loupe, comparing stellar brightnesses plate by plate with meticulous precision. Over the course of years, she catalogued first 1,777 variable stars in the Magellanic Clouds, and then, in her landmark 1908 paper, noted something that would change everything. The Cepheid variables among her catalogued stars showed a clear, measurable relationship between their period of pulsation and their apparent brightness. Longer periods correlated with greater brightness. Since all the stars in the Magellanic Clouds are approximately the same distance from Earth, the cloud is so far away relative to its own depth that the depth itself is negligible. The apparent brightness difference between Leavitt's Cepheids reflected their actual intrinsic brightness difference. Period equaled power. The longer the pulsation, the more luminous the star. Leavitt published her findings in 1912, noting explicitly that the relationship could serve as a distance measurement tool of extraordinary potential. She wrote, with characteristic scientific restraint, "A straight line can readily be drawn among each of the two series of points corresponding to maxima and minima, thus showing that there is a simple relation between the brightness of the variables and their periods." She did not advertise the cosmological implications. She let the mathematics speak. What the mathematics said was this: if you can observe a Cepheid variable anywhere in the universe, measure its period, and compare its apparent brightness to the intrinsic brightness predicted by the period-luminosity relationship, you can calculate the exact distance to that star, and to anything nearby it. Leavitt died in 1921 of cancer, 2 years before Edwin Hubble used her period-luminosity relationship to identify the first Cepheid variable in Andromeda and calculate its distance. She never knew that her work would be the key that opened the universe. She never knew that every measurement of cosmic distance for the following century would depend on the relationship she had found on glass plates in a poorly lit room in Cambridge, Massachusetts. In 2013, the Royal Swedish Academy of Sciences, which awards the Nobel Prize, reportedly inquired about the possibility of nominating Leavitt for the award. The inquiry was made before the Academy learned that she had been dead for decades. The Nobel Prize is not awarded posthumously. The question of whether Leavitt would have received the award she undeniably deserved had she lived longer is one of those counterfactual questions that astronomy historians have wrestled with ever since, and that does not have a satisfying resolution. What her work gave us, ultimately, through the chain of reasoning that runs from her Magellanic Cloud observations, through Hubble's 1923 glass plate to the decade-long PH-HAT and PH-HAST surveys, was the ability to measure distances across the universe with the precision required to understand everything that follows. Without Leavitt's period-luminosity relationship, Hubble had no standard candle. Without a standard candle, Andromeda's distance was unknown. Without its distance, nothing about Andromeda's scale, its stellar populations, or its history could be correctly calibrated. The modern heir to her method, the beneficiary of the century of cosmic distance measurement that she made possible, is a man named Nicholas Lehner, a professor of astrophysics at the University of Notre Dame in Indiana, who spent years staring at Andromeda from an entirely different direction, not at its stars, at its gas. And what he found in that gas represents what I regard as one of the most disorienting scale revelations in the history of astronomy. Lehner's interest was in the circumgalactic medium, the diffuse, largely invisible envelope of ionized gas that surrounds a galaxy well beyond its visible stellar disk. The circumgalactic medium, or CGM, is the vast ocean of plasma through which galaxies breathe. It is the reservoir from which they draw fresh gas to fuel star formation, and the dumping ground into which supernovae and stellar winds expel processed, heavy element-enriched material. It is, in a real sense, the life support system of a galaxy, and for most of astronomical history, it was essentially undetectable, too tenuous and too diffuse to show up in any conventional observation. Lehner and his collaborators developed a method to probe Andromeda's CGM indirectly. The technique works by using quasars, the brilliantly luminous, incredibly distant cores of active galaxies powered by supermassive black holes, as backlit probes. When the light from a distant quasar travels through the CGM of a foreground galaxy on its way to our telescopes, the gas in the CGM absorbs certain specific wavelengths of that quasar's light, leaving characteristic dips in the quasar's spectrum. By measuring those absorption signatures, and by knowing the physical properties of the gas species that produce them, carbon, silicon, oxygen, you can infer the temperature, density, composition, and extent of the CGM. The challenge with this technique when applied to distant galaxies is that you typically have only one or two suitable background quasars aligned by coincidence with the galaxy's halo. A single sightline gives you a single probe point. That is like trying to understand the three-dimensional structure of an ocean by measuring the temperature of the water at a single location. You learn something, but not nearly enough. This is where Andromeda's unique proximity became, for the first time, a tool of circumgalactic science rather than just stellar science. Because Andromeda's halo, if it existed and was sufficiently extended, would loom enormous on the sky, covering a vast area of the celestial sphere. And behind that enormous area, there were dozens of suitable background quasars, distributed across the halo's extent like scattered lighthouse beams shining through a fog. Lena's team identified 43 of them for their study, called Project Amiga, absorption maps in the gas of Andromeda, using Hubble's cosmic origin spectrograph, which is sensitive to the ultraviolet wavelengths at which ionized carbon, silicon, and oxygen absorb most efficiently, and which Earth's atmosphere renders completely unobservable from the ground. The team spent years accumulating spectra of all 43 quasars, measuring the absorption signatures of Andromeda's gas in each one. In 2015, Lena published the first results, a detection of a large, massive halo of ionized gas around Andromeda that extended to at least 300 light-years from the galaxy's centre. That was already remarkable, a gas halo 10 times the radius of the visible stellar disk. But the coverage was still limited. In 2020, the full Project Amiga results arrived, based on the complete 43 quasar dataset. And the numbers in that paper were, to use the precise scientific term, jaw-dropping. Andromeda's circumgalactic medium extends to at least 3 million light-years from the galaxy's centre. In some directions, the outer reaches of the halo stretch to more than 2 million light-years. To put this in perspective, Andromeda's stellar disk, the part you can see as a faint oval in the autumn sky, is approximately 152,000 light-years across. The gas halo surrounding that disk is, in its maximum extent, more than 26 times larger in radius than the visible galaxy. If Andromeda's CGM were somehow rendered visible to the naked eye, if the tenuous plasma of its outer halo emitted light at visible wavelengths, it would appear on the night sky as a structure approximately 3 times the angular width of the Big Dipper. It would be the single most prominent object in the entire night sky, dominating the constellation Andromeda and its neighbours. The halo also has structure. It is not a uniform sphere of diffuse gas. Lena and his team found that it has 2 distinct nested shells, an inner region extending to approximately 500,000 light-years, which is more dynamic, more complex, and richer in heavy elements. Contaminated by the outflows of supernovae, the chemical aftermath of billions of years of stellar death, and an outer shell that is smoother, hotter, and less enriched, representing a more primordial component of the halo that has been less processed by stellar activity. But the finding that carries the highest stakes is not the size of the halo, it is the distance to its outer edge. Because 3 million light-years, remember, is roughly half the distance between Andromeda and the Milky Way. Andromeda's circumgalactic medium already extends more than halfway to us, and in its most extended regions, reaching 2 million light-years from M31 Center, it is very nearly all the way. The halos of Andromeda and the Milky Way are right now beginning to overlap, 2 vast gaseous envelopes, each containing more total mass in diffuse plasma than in visible stars, already reaching for each other across the intergalactic void. Andromeda's halo is already bumping into the halo of our own galaxy, Lena told NASA in the official release of his team's findings, and then added something that carries the weight of all those photographic glass plates and all those years of patient measurement behind it. This is truly a unique experiment. Only with Andromeda can we do this. The personal cost embedded in this story is quieter than a single dramatic moment of discovery. It lives in the years Lena spent building the argument, in the grant applications, the telescope time proposals, patient accumulation of quasar spectra one at a time, sustained by the conviction that the answer was out there, hiding in the ultraviolet absorption lines of 43 distant quasar beams. It lives in the image of Henrietta Leavitt at her magnifying loupe, cataloguing variables on glass plates for 30 cents an hour, building the measuring tape that would eventually let someone like Lena prove that the nearest large galaxy to our own already touches us with invisible hands. Science is not a series of individual moments of revelation. It is a relay race run across generations, each runner adding their distance to the one before, never seeing the finish line, trusting that it is there. Leavitt handed her period luminosity relationship to Edwin Hubble. Hubble handed the universe's true scale to the 20th century. The 20th century handed Hubble the telescope. Hubble the telescope handed Lena 43 quasar sightlines, and the ultraviolet spectrograph to read them, and Lena handed us the knowledge that Andromeda's reach has already crossed the halfway point. We are not watching a distant galaxy approaching us. We are already inside it. Everything discovered so far about Andromeda, its violent merger history, its anomalous star formation record, its stripped satellite ghost, the impossible blue disk around its central black hole, the invisible gas halo already touching the Milky Way, all of it is prologue, because the most consequential event in Andromeda's relationship with the Milky Way has not yet happened. It is happening in slow motion across timescales so vast they are almost incomprehensible, but its outcome, when it arrives, will be the most dramatic single event in the history of our galaxy since the solar system formed. Andromeda and the Milky Way are falling towards each other. This has been known for decades. The radial velocity of Andromeda relative to the Milky Way has been measured at approximately 110 kilometers per second in fall along the line of sight. That is not a slow drift. That is a closing speed of roughly 396,000 kilometers per hour. The distance currently separating the two galaxies is 2.537 million light-years, a number so large that at 110 kilometers per second, it still takes billions of years to close, but close it does. The gravitational attraction between two masses each on the order of 1 trillion solar masses, across a gap of 2.537 million light-years, is irresistible on cosmological timescales. What began as an expanding separation in the early universe, when the universe's overall expansion was carrying all matter apart from all other matter, has reversed. These two galaxies are now in each other's gravitational grip, falling together on a trajectory that will end in one of the universe's most spectacular events, a galaxy merger. The timing and nature of this merger became significantly sharper in 2012 when a team using Hubble's precise astrometric capabilities measured for the first time not just the radial component of Andromeda's motion, how fast it is moving towards or away from us along our line of sight, but the transverse component, how fast it is moving sideways across the sky. This distinction matters enormously, because the transverse velocity determines whether Andromeda will hit us head-on, graze us in a glancing blow, or miss us entirely. The measurement required Hubble to measure the positions of stars in Andromeda over a period of approximately 7 years, detecting a proper motion, a sideways drift on the sky, of approximately 0.0005 arcseconds per year. This is the angular equivalent of measuring the width of a human hair from a distance of approximately 2,000 kilometers. The results indicated that Andromeda is indeed on a path that will bring the two galaxies into direct collision, beginning in approximately 4.5 billion years from now. Earlier estimates had suggested a potential glancing encounter. The Hubble transverse measurement tightened the prediction considerably. The collision was confirmed as substantially head-on, with the two galactic disks encountering each other in an interpenetrating event that will reshape both galaxies completely. However, and this is a critical qualification that the popular science press frequently glosses over, the collision of two galaxies is not the collision of two solid objects. The distances between individual stars within each galaxy are so enormous that the probability of any two specific stars actually colliding during the merger is essentially zero. As the two galactic disks interpenetrate, the vast majority of stars, including the Sun, will simply fly past each other on altered gravitational trajectories, like two swarms of bees passing through each other. The galactic collision will be spectacular in terms of tidal forces, gas dynamics, triggered star formation, and the ultimate gravitational rearrangement of both galaxy structures. But it will not be a physical impact in any sense familiar to human experience. The simulations of the Andromeda-Milky Way merger, run on supercomputing clusters and refined over multiple generations of cosmological modelling, paint a picture of extraordinary dynamism. The first close approach, which most models place at roughly 3.9 to 4.5 billion years from now, will trigger massive tidal distortions in both galactic disks. Immense stellar streams, similar to the ones already visible in Andromeda's halo from its previous merger with M32P, will be flung out into the surrounding intergalactic medium. The compressed gas clouds in both galaxies' disks will collide and shock compress, triggering waves of star formation across both systems simultaneously. The two central supermassive black holes, Andromeda's 140 million solar mass engine and the Milky Way's 4.1 million solar mass Sagittarius A, will eventually be drawn together in a slow, spiraling-in spiral driven by dynamical friction, ultimately merging to form a single black hole of combined mass somewhere in the range of 150 million solar masses. As the two galaxies merge, the combined system will undergo what is called a galactic starburst, a period of intensified star formation triggered by the compression of gas clouds, followed by a progressive exhaustion of the gas reservoir. Over a period of perhaps 2 billion years following the initial encounter, the combined system will undergo multiple passes, each one distorting both galaxies further until the two cores finally merge into a single gravitational center. The end product will be a giant elliptical galaxy, sometimes nicknamed Milkomeda or Milkdromeda in the informal literature, a featureless football-shaped system of old, red stars, its gas reservoir depleted, its star formation days essentially over. The night sky during this process, for any observers that might exist on Earth or its descendants, will be transformed beyond recognition. As the two galaxies approach, Andromeda's visible disk will begin to grow larger on the sky, brightening slowly over millions of years. As the first close approach occurs and tidal forces distort both disks, the sky will fill with vast arcs of stars, stellar streams extending across enormous angular scales, the entire celestial sphere becoming a dynamic spectacle of intergalactic encounter. The two galactic planes, currently separated by the enormous distance that makes Andromeda's disk so faint, will begin to overlap, filling the night sky with light from hundreds of billions of new neighbours. If life persists on Earth or any of its successor civilizations that long, the Sun will be in its late main sequence phase, roughly 8 to 9 billion years old, and will have another 500 million years before it begins to swell into a red giant. The view from any habitable world in the merged system will be among the most spectacular in the universe. But there is now a significant challenge to this entire scenario, and it emerged as recently as 2025. A study published in Nature Astronomy by Pham et al. Used updated proper motion measurements from the Gaia Space Telescope's third data release to recalculate Andromeda's transverse velocity with unprecedented precision. Their results introduced a genuine uncertainty into the collision timeline. The updated Gaia measurements suggest that Andromeda's transverse velocity may be higher than Hubble's earlier measurement indicated, meaning the galaxy may have more lateral motion relative to the Milky Way than previously calculated. A higher transverse velocity changes the orbital geometry of the encounter. In the extreme case, a large enough transverse motion could convert what was expected to be a head-on collision into a grazing pass, or, in the most extreme scenario, into a non-merging flyby. Pham et al. Reported approximately a 50% probability that the two galaxies will not actually merge within the next 10 billion years. This does not mean the collision has been ruled out. The measurement uncertainties are still substantial, and the gravitational dynamics of two-body systems of this mass, at this distance, over these timescales, are sensitive to parameters that remain imprecisely constrained. But it does mean that the merger scenario is now statistically less certain than it appeared in 2012, and that the fate of the Milky Way and everything in it is genuinely unresolved. The irony here is exquisite and genuinely unsettling. The same Hubble survey that revealed Andromeda's merger history, the collisions that shaped M31's past, has contributed to an uncertainty about whether we ourselves will undergo a similar fate. We can read the scars of past galactic collisions written in the ages of Andromeda's stars with extraordinary precision. We cannot yet determine with certainty whether we are going to be added to that record. There is something I find genuinely haunting about that asymmetry. We know what happened to Andromeda. We do not know what will happen to us. And the evidence that allows us to read Andromeda's past is the same evidence that highlights the uncertainty of our future. The collision scenario, and the question of whether it will happen, is not even the most scientifically challenging consequence of Hubble's Andromeda findings, because the revelations from the PIET and PIEST surveys, combined with the Project Amiga Halo data and the peculiar discoveries at Andromeda's core, raise a question that cuts deeper than any single merger event. They raise a question about galaxy evolution itself, about whether the models we have built to describe how spiral galaxies live and die are actually correct, about whether Andromeda's story is exceptional, or whether the Milky Way is the one that is unusual. In the language of extragalactic astrophysics, there is a word that carries enormous weight: quenching. When astronomers say that a galaxy has been quenched, they mean that its star formation activity has been suppressed, reduced to a fraction of what it once was, or shut down altogether. Quenching is not a small adjustment to a galaxy's lifestyle. It is a transformation of fundamental character. A star-forming galaxy is blue-white, luminous, full of hot young stars burning through their hydrogen fuel at profligate rates. A quenched galaxy is red, passive, increasingly dominated by old red and yellow stars as its youngest, hottest members age and die without being replaced. Over cosmological timescales, quenching is the process that converts a star-forming spiral galaxy into a dead elliptical, the most common type of galaxy in the modern universe, and by far the most common in the dense regions of galaxy clusters. The quenching problem is one of the most active areas of research in modern astrophysics. How does a galaxy stop forming stars? What shuts off the supply of cold gas that is the raw material for new stellar birth? Several mechanisms have been proposed, and each one operates on different timescales, at different scales, and through different physical channels. Feedback from a supermassive black hole at the galaxy's centre, what astronomers call AGN feedback, can heat or expel the surrounding gas, preventing it from cooling and collapsing. Supernova explosions across the disk can drive powerful winds that sweep gas out of the galaxy. Tidal stripping in dense environments, when a galaxy passes through the hot gas of a galaxy cluster and has its own gas reservoir ram pressure stripped away, can rapidly quench star formation in satellite galaxies, and major merger events, as discussed, can trigger an extreme starburst that burns through the galaxy's gas reservoir in a short, violent episode. What makes Andromeda scientifically valuable in the context of the quenching problem is that it appears to be a galaxy in the process of being quenched, not yet fully passive, but clearly partway through the transition, without sitting in the dense environment of a galaxy cluster where environmental mechanisms would be expected to drive quenching. Andromeda is a field galaxy sitting at the centre of the relatively sparse local group, far from any dense cluster environment. Environmental quenching mechanisms should not apply to it, and yet the evidence from the PIAT and PS data suggests that its star formation rate is lower than expected for a galaxy of its mass and gas content, and that the suppression began following the merger with M32P's progenitor galaxy. This points directly to merger-driven quenching as the dominant mechanism in Andromeda's case. The collision with M32P, the simulations suggest, triggered a burst of star formation across Andromeda's disk, a wave of gas compression that ignited new stellar nurseries across an enormous area. This starburst phase, intensified and relatively brief on cosmological timescales, burned through a significant fraction of Andromeda's available cold gas reservoir. Following the starburst, the gas supply was depleted and the star formation rate fell. Additionally, the tidal disruption of M32P's disk would have transferred significant kinetic energy into Andromeda's disk, heating the gas and making it harder for new cold filaments to condense and form molecular clouds, the prerequisite for new star formation. The combined effect was a galaxy that emerged from the collision phase with less fuel and a harder time making more, now slowly fading from spiral towards elliptical. The Milky Way, by contrast, appears to have avoided this fate. Its star formation history shows no equivalent burst and suppress pattern. Its stellar disk is more uniformly populated with stars of a broad range of ages, without the anomalous young star excess that marks Andromeda's disk. It has experienced its own suite of minor merger events. The Sagittarius dwarf spheroidal galaxy, currently being shredded and incorporated into the Milky Way's halo, is one ongoing example, but none of a magnitude comparable to the M32P collision. As a result, the Milky Way retains a more intact cold gas reservoir and continues to form stars at a steady, moderate rate. This difference between the two galaxies, the Milky Way's relative quiescence versus Andromeda's partial quenching, has significant implications for the conventional astronomical narrative that has treated them as twins. They are not twins. They are at minimum fraternal siblings who took dramatically different paths through the same cosmological neighbourhood, one experiencing a transformative galactic collision that the other avoided. Understanding why one of these two dominant galaxies of the local group was struck and the other was not. A question of orbital geometry, timing, and the initial distribution of mass within the local group is a key unsolved problem in nearby galaxy evolution. There is a deeper layer to this, however, one that the pH and pH-ACE data are only beginning to illuminate. The question of when, exactly, the merger with M32P's progenitor occurred, and how precisely it maps onto the anomalous stellar populations revealed by the survey is still being actively worked out. The 2018 D'Souza simulations placed the major encounter at roughly 2 billion years ago, but the error bars on this estimate are large. The pH-PAT data can independently constrain the timing by reading the ages of the anomalous stellar populations. If there was a starburst triggered by the collision, there should be a population of stars formed during that episode whose ages cluster around the same epoch, identifying that population cleanly, separating it from the background of Andromeda's own continuous star formation history, requires the kind of detailed stellar age resolution that only the full PATE-HAS dataset can provide. The results from this stellar archaeology are still being extracted, paper by paper, from the enormous dataset. But the preliminary picture is consistent. There is an excess of stars in Andromeda's disk whose ages fall in the range of 2 to 4 billion years, concentrated in spatial distributions that are asymmetric and streaky in a way that is consistent with accretion from a disrupted satellite. Exactly what a merger with M32P's progenitor 2 to 4 billion years ago would have left behind. This is not yet a definitive chronology, but it is pointing compellingly in one direction. Meanwhile, a completely separate line of evidence, also derived from Hubble observations focused on the very smallest scale structures at the other end of the mass spectrum from entire galaxies, has revealed yet another complication in the Andromeda story, a complication that connects Andromeda's history to one of the most contested questions in black hole astrophysics. In 2023, astronomers at the University of Utah announced the confirmation of an intermediate mass black hole inside a massive stellar cluster in Andromeda's halo. The object, designated B023G078, had been suspected of harbouring an unusually massive dark object for some years, but the Utah team's analysis, using both Hubble Space Telescope imaging and Keck Observatory spectroscopy to measure stellar velocities within the cluster, provided the most robust evidence yet for a black hole of approximately 100,000 solar masses. This is significant because intermediate mass black holes, objects in the mass range between stellar mass black holes, a few to a few dozen solar masses, and supermassive black holes, millions to billions of solar masses, represent one of the most theoretically important but observationally elusive classes of objects in astrophysics. The leading theory for how supermassive black holes formed in the early universe involves a process called hierarchical merging. Small black holes merge to form intermediate mass black holes, which then merge to form supermassive black holes. If this pathway is correct, intermediate mass black holes should be common. They are the middle rungs of the ladder, but confirmed detections of them are extraordinarily rare. Most candidates have come from indirect evidence, with alternative explanations remaining viable. The B023G078 black hole is significant because the confirmation methodology was strong enough to rule out the most common alternative explanation, that the measured stellar velocities could be accounted for by a dense concentration of ordinary stellar remnants rather than a single massive compact object. The mass distribution of B023G078's stellar population and the way stellar velocities rise towards the cluster's centre is consistent with a black hole of approximately 100, zeros in solar masses, and inconsistent with any plausible configuration of stellar remnants. What does this intermediate mass black hole have to do with Andromeda's merger history? Possibly quite a lot. B023G078 is a massive stellar cluster, classified as either a globular cluster or the stripped nucleus of a dwarf galaxy, sitting in Andromeda's halo at a distance of approximately 60 light-years from the galaxy's centre. Its classification as potentially the stripped nucleus of a dwarf galaxy is significant. It makes B023G078 a possible miniature version of the M32 story, another remnant core of a galaxy that was stripped of its outer layers by tidal interaction with Andromeda. If so, it represents additional evidence of Andromeda's habitual violence, another entry in a pattern of galactic consumption that the full-fat T-HAST survey is now revealing in its broader context. There is also a theoretical connection between the B023G078 intermediate mass black hole and Andromeda's central supermassive black hole. According to hierarchical black hole growth models, Andromeda's 140 million solar mass central black hole built up its current mass partly through the accretion of infalling gas and partly through mergers with smaller black holes carried in by infalling satellite galaxies. Every time Andromeda consumed a satellite galaxy, any black hole at that satellite's core was dragged in by dynamical friction, spiralling inward toward M31's centre and eventually merging with it. The blue disk of stars at Andromeda's core formed 200 million years ago in an apparently impossible burst of star formation right next to the central black hole, may be the most recent sign of this process, triggered by a fresh accretion event or a gravitational perturbation from an infalling object. But the blue disk itself raises a question that the PAT-PAST surveys and the intermediate mass black hole discovery together intensify rather than resolve. If star formation at Andromeda's nucleus was triggered by an event 200 million years ago, what was that event? Was it connected to the larger collision history? Was it a separate, more recent perturbation? Was it driven by infalling gas from the circumgalactic medium mapped by Project Omega, raining down onto the galaxy's centre from its enormous halo? The timing does not obviously match the major merger event 2 billion years ago. It is too recent, which means it was either triggered by a separate, smaller interaction, a dwarf galaxy falling in from Andromeda's satellite population, or it reflects a periodic process, one of a series of star formation episodes that have occurred repeatedly at Andromeda's nucleus throughout its history, driven by some recurring mechanism that has not yet been identified. This is where the story currently stands. Not resolved, not closed, a set of discoveries that fit together into a broad picture of a violent, active, complicated galaxy, but with critical details still missing, still contested, still being extracted from the data. The PAT and PAST mosaic represents the foundation of the next 20 years of Andromeda science, the specific discoveries it will enable, the precise chronology of the M32P merger, the identification of accreted stellar populations versus in situ formed ones, the connection between the halo structures mapped by Project Omega and the disk structures mapped by the stellar surveys, are questions that are actively being worked on by dozens of research groups right now, which leads to the most forward-facing question of all. What comes next for Andromeda science? And what does everything we have found out about Andromeda tell us about where the Milky Way stands and where it is headed? In January 2025, when the combined PTAST mosaic was announced to the world, Ben Williams of the University of Washington, the principal investigator of the survey, made a remark that captured both the achievement and the horizon beyond it, with admirable concision. With Hubble, we can get into enormous detail about what's happening on a holistic scale across the entire disk of the galaxy, he said. You can't do that with any other large galaxy. And then, almost in the same breath, he and his co-investigators began describing what comes next. Observations with the James Webb Space Telescope, which can see deeper into the infrared than Hubble, detecting cooler stars and penetrating the dust lanes that obscure portions of Andromeda's disk. And observations with the Nancy Grace Roman Space Telescope, whose wide-field camera will capture an image equivalent to more than 100 high-resolution Hubble frames in a single exposure. Roman is scheduled for launch in 2027. Its wide-field infrared survey camera, with a field of view approximately 200 times larger than Hubble's Wide-Field Camera 3, will make the enormous decade-long stitching project that produced the 5 billion pixel past mosaic look by comparison like a weekend exercise. Roman will image not just Andromeda's disk but its entire extended halo, the outer stellar structures, the tidal streams, the accreted populations that extend beyond the disk's visible edge, at a resolution and depth that will transform the stellar archaeology of M31 from a difficult, multi-decade project into something routine. This matters because the outer halo of Andromeda, which Hubble's survey only partially covered, contains the most direct record of the galaxy's merger history. Every satellite galaxy that has ever fallen into Andromeda and been tidally disrupted has left a traceable stream of stars in the outer halo, a river of suns on similar orbits, slowly dispersing over billions of years, but still detectable as coherent structures by a telescope sensitive enough to resolve individual stars at Andromeda's distance. Mapping these streams in their entirety, their spatial distribution, their chemical compositions, their stellar ages, will allow astronomers to reconstruct the full merger history of Andromeda from the present day back to its earliest encounters, building an N-body history of the galaxy across its entire lifetime. The James Webb Space Telescope, meanwhile, is already contributing. Its infrared capabilities allow it to peer through the dust lanes that line Andromeda's spiral arms, regions where the interstellar medium is dense enough to absorb and scatter visible light, blinding Hubble to the stellar populations within. The star-forming regions along Andromeda's ring of star formation, a prominent structure at approximately 30,000 light-years from the galaxy's centre, thought to be a relic of the collision with M32P, a density wave driven through the disk by the impact, are rich in embedded young stellar objects, protostars still wrapped in their natal dust cocoons, invisible to Hubble but luminous in the infrared. Webb will map these in detail, connecting the current generation of star formation in Andromeda's disk to the fossil record of past generations uncovered by PAT and PAST. There is also the question of Andromeda's supermassive black hole. The confirmation of its 140 million solar mass, achieved through the velocity dispersion of the blue disk of stars, was a landmark result. But the mechanisms that formed the blue disk, stars created in defiance of the tidal disruption limit, remain unexplained. Future observations with the next generation of space telescopes, particularly any ultraviolet successor to Hubble, will be needed to characterize the disk's detailed structure and the gas dynamics of the nuclear region at higher resolution. The question of how stars form right next to a 140 million solar mass black hole is not an idle curiosity. It is a question about the fundamental limits of stellar physics in extreme environments. Environments that, as Lauer noted, may not be unusual. Our own Milky Way's galactic centre, with its peculiar young stellar populations within a few light-years of Sagittarius A, shows the same pattern. Understanding one may be the key to understanding both. The Project Amiga successor, a program that Lena and collaborators have called for in multiple recent papers, would require a large ultraviolet telescope in space to continue mapping Andromeda's circumgalactic medium with even greater sightline density. The 43 quasar sightlines of the current survey represent a significant sampling, but the inner CGM, within roughly 100,000 light-years of the galaxy's centre, inside the radius where disk processes and halo processes interact most intensively, remains sparsely characterized. Understanding how gas flows from the outer halo into the disk to fuel star formation, and how supernovae-driven outflows from the disk enrich the inner halo, requires a three-dimensional map of the CGM's composition and structure at a density of sightlines that only a next-generation ultraviolet observatory can provide. And then there is the collision, a question of whether the Andromeda-Milky Way merger will actually occur, rendered newly uncertain by the Gaia proper motion measurements of 2025, requires the next generation of astrometric data to resolve. Gaia's final full data release, combined with future missions capable of measuring proper motions with even greater precision, will progressively tighten the uncertainty in Andromeda's transverse velocity. Within the next decade, the probability distribution on the merger outcome will narrow significantly. We will know, with considerably better confidence than we do today, whether the night sky of our distant descendants will be dominated by the spectacle of an approaching galaxy. But perhaps the most profound implication of everything Hubble has found in Andromeda goes beyond any individual discovery or observational program. It is a conceptual implication, a change in how we understand our own position and our own galaxy's history. Because if Andromeda and the Milky Way are not twins, if they have taken divergent paths through the same cosmological neighbourhood, then using Andromeda as a proxy for the Milky Way, as astronomers have done for a century, needs to be done with considerably more care. The differences between the two galaxies are not noise to be averaged away. They are signal. They are telling us something about the role of environment, timing, and chaotic chance in determining the evolutionary trajectory of a spiral galaxy. What Hubble found inside Andromeda was, ultimately, a story about contingency, about the fact that the broad cosmic framework, the laws of physics, the initial conditions of the Big Bang, the cosmological parameters that determine how structures form, provides the stage and the rules, but the specific outcome for any particular galaxy in any particular location depends on which other galaxies happen to be nearby, at what velocity, on what orbital trajectory, with what mass. The Milky Way's relative calm is not a guarantee. It is a historical accident. The path not taken is illustrated in extraordinary detail by Andromeda's scars, by M32's stripped ghost, by the anomalous blue stars orbiting an impossible disk around a 140 million solar mass engine, by a gas halo already reaching for us across 1.3 million light-years of dark intergalactic space. We are looking at our own possible future, written in the past of our closest galactic neighbour. And the future it depicts is neither catastrophic nor serene. It is transformative. It is the universe doing what it has always done, building things up, tearing them apart, and making something new from the wreckage. On that clear October night in 1923, Edwin Hubble stood at the eyepiece of the Hooker telescope and saw a single star winking at him across 930,000 light-years of space. He wrote VAR on a glass plate and changed the universe. But there is a detail about that moment that is easy to overlook. The light that entered Hubble's telescope that night, the light that struck the photographic emulsion of plate H335H and registered as a tiny, measurable variation in brightness, had not left Andromeda in 1923. It had left Andromeda 930,000 years earlier, in an epoch so remote that anatomically modern humans had barely existed long enough to leave any archaeological record. We were, in the most literal sense, looking at the past. We have always been looking at the past. Every photon from Andromeda that has ever struck a human eye, or a telescope mirror or a photographic plate, is a message in a bottle from a civilization of stars that sent it before we existed. The light that the Hubble Space Telescope captured in its decade of P8 and P-H observations, the light that built the 2.5 billion pixel mosaic that revealed the anomalous stellar populations and the merger scars and the impossible blue disk around the central black hole. that light left Andromeda's stars 2.537 million years ago when our ancestors were walking the savannas of Africa with stone tools and the galaxy above them was an uninterpreted smear. The universe does not deliver news, it delivers archaeology. Everything we see is evidence of what was, not what is. This is not a limitation to be lamented. It is, in a strange way, the universe's most generous gift to science. The fact that light takes time to travel means that we can look outward and look backward simultaneously. The further we look, the older the evidence. The entire history of the cosmos is written in the sky above us, in layers, like the sediment of a geological record, and we have been reading it a little more clearly with every generation, for as long as we have been capable of asking why. What Hubble found inside Andromeda has shocked scientists not because it is unprecedented in the abstract sense. Galaxy mergers happen everywhere. Supermassive black holes have impossible disks in dozens of systems we have observed. Circumgalactic halos are universal, but because it happened here, to our closest large neighbour, to the galaxy that we assumed was our twin, our proxy, our comfortable mirror. The revelation that Andromeda is a train wreck, beautiful, luminous, exquisitely detailed, and fundamentally traumatized, forces a reckoning with the assumption that the Milky Way's relative peace is the cosmic norm. It may be. Or it may be that the Milky Way is the exceptional case, the spiral that has, so far, avoided the encounter that would send it down Andromeda's path. We do not know yet, and that not knowing is not a failure of science. It is the most honest and productive place that science can occupy. At the edge of what is understood, staring into what isn't. There is a version of this story that ends with a reassuring summary. Here is what we found, here is what it means, here is where we stand. But that would be the wrong ending, because the 2.5 billion pixel mosaic released in January 2025 is not a conclusion. It is a foundation. The papers, currently being written from the PAT and PASS datasets, will be cited for decades. The stellar age distributions encoded in those 200 million catalogued stars have not yet been fully deciphered. The precise chronology of Andromeda's merger history, when M32P fell in, how the collision reshaped the disk, what triggered the blue stars around the central black hole, is still being assembled, one careful analysis at a time, and somewhere in that data, in the distribution of stellar ages across Andromeda's disk, in the chemical compositions of the stars in its tidal streams, in the absorption signatures of the gas, in its circumgalactic halo, there may be the answer to the question that drives all of this. Not what Andromeda looked like, not what it has been through, but what the Milky Way will look like in 2 billion years, in 4 billion years, in the epoch after the merger, when our galaxy has either been transformed into something unrecognizable or emerged from the encounter still, impossibly itself. Edwin Hubble wrote VAR on a glass plate and gave us the universe. The universe, it turns out, is under no obligation to be what we expect. It is only obligated to be what it is. We are still learning what that is. The next discovery is already waiting in the data.